We can continue to the second question. Consider a problem in engineering that is required to solve using a numerical method. Use the A5 to deal or solve this problem. So we can start by the first problem. So the first problem is how to measure the fluid mechanics problem. So the intention, solve a fluid mechanics problem using a numerical method. And the initial thinking, solve fluid flow through a pipe using a numerical method such as finite element method. The idealization is the ideal solution would be an accurate simulation of fluid flow with velocity and pressure profiles validated by experimental results. We can continue the instruction set. Clearly define the engineering problem, including parameters such as pipe geometry, fluid properties, and flow conditions. Break down the problem into smaller, manageable parts, then identify boundary conditions, initial conditions, and relevant physical flows. Imagine an ideal computational model that perfectly replicates the physical phenomenon without numerical errors. Develop a numerical method using FEM software such as ANSYS and GFDsoft. Set up the mesh, boundary conditions, and initial conditions. And then we can run the simulation and refine the mesh if necessary. So we step to the next problem. It's about a heat distribution in metal plate. The intention is the goal to understand and predict the temperature distribution across a metal plate subjected to different heat sources and boundary conditions. This information is crucial for applications in thermal management and materials engineering. Initial thinking. The metal plate is heated at certain points, while other edges are kept at a constant temperature. Understanding how heat distributes over time can help in optimizing cooling strategies in electronic components or manufacturing process. Idealization. Imagine an ideal scenario where we have a perfect model that can predict the temperature at any point in the plate with high accuracy and in real time. This model would consider all physical properties and boundary conditions perfectly, providing insights that can be directly used to improve thermal designs. We can step to the next instruction set. First, define the geometry and mesh, and then set initial and boundary conditions, and then discretize the heat equation, and then develop the numerical algorithm. And we can run the simulations. So we continue to the last problem. It's about the structural deformation of a beam under load. So the intention is to analyze and predict the deformation and stress distribution in a beam subjected to various loads. This analysis is crucial for ensuring structural integrity and safety in civil and mechanical engineering applications. About the initial thinking is to determine how a beam deforms under a specific load. Understanding the stress distribution and deformation can help in designing safer and more efficient structures. The idealization is an ideal scenario. The numerical model would accurately predict the deformation and stress distribution with high precision. This model would consider all physical properties and loading conditions perfectly, providing insights that can be directly used to optimize structural designs. And the instruction set: create a finite element mesh representing the beam. The finer the mesh, the more accurate the results. But this also increases computational cost. And then we define the material properties of the beam, such as Young modulus and Poisson ratio. Then we implement the FEM algorithm in a programming language like Python or MATLAB. Solve the system of equations obtained from the stiffness matrix to find the nodal displacements. Then we run the simulations.